This conference will now be recorded.
All right, this is Math 211, Section 2.5, Extra Examples. So we're looking at a few of them that we had to skip over in class. The first one is in Example 1. We're looking at this part E. You could turn this into a quotient rule if you wanted to by moving this to the denominator because of the negative exponent, or you can still treat this as a product rule as it is. So I'm actually going to do that. It works out pretty nicely that way. So our first function is 3t minus 1 to the fourth, and its derivative would be 4 parentheses 3t minus 1 to the third times the chain of the inside, which is a 3. So that makes that 12 3t minus 1 to the third. The second function is 2t plus 1 to the negative 3, and its derivative is going to be negative 3 2t plus 1 to the negative 4 when we subtract a power times a chain of 2, and that makes this one negative 6 2t plus 1 to the negative 4. So if we go to write our product rule here, we would have f, big F prime of t is equal to the first times the derivative of the second, and then plus the second function times the derivative of the first, and then I would use skills that we have in Math 136 of factoring out a GCF here. So you can pull out a 6 from the common monomials. You can pull out 3t minus 1 to the third power. That's what they have in common. And when there's a negative exponent, you pull out the smaller of the two exponents, which actually is negative 4. And the reason we do that is that when we pull it out, we're really dividing, and that makes this pretty much go away. But when you do negative 3 minus a negative 4, because when you divide two things that are same base but they have exponents, you subtract those exponents. That makes negative 3 plus 4, which ends up being a 1, so it makes it work out nicely. So then this would leave me with just a negative 1, because I didn't pull out the negative sign there. And then I would have a 3t minus 1 to the first power, plus 12 divided by 6 is 2, and I would still have a 2t plus 1 to the first power. Now I would want to work out the inside portion here, and I'm also going to move this part that has the negative exponent to the denominator. So right now I have a 6 times a 3t minus 1 to the third, and then I'm going to have on the bottom a 2t plus 1 to the fourth, and up top we're going to have a negative 3t and a plus 4t, so that's going to be just 1t, and we have a positive 1 and a positive 2 when we distribute, so that's going to be positive 3. So there is my derivative of that function. Now this next portion, we want to just make sure we're careful with notation and sine, cosine, tangent with dealing with exponents. So you just have to be really careful and pay attention to what you see. Remember, sine squared of x actually means that we're doing d dx, derivative with respect to x, of a sine x that has been squared. So we're using the general power rule to pull that 2 to the front. We have our sine x to the now first power essentially, and we chain on the derivative of the inside of that base, which was sine, so that's going to be cosine x. Now if you recognize this, 2 sine x cosine x can also be rewritten as sine of the double angle x, so 2x. For this next one, notice this is not squaring the whole sine, this is a square on just the x. So this is d dx of sine of x squared. So we do the outside function is the sine function here, so the derivative of that is cosine, keep the guts the same, and then we would times it by the chain of the inside, which is 2x. So you could rewrite that as 2x cosine of x squared. This one, this is tan squared, which we can remember right with the squared on the outside, but the inside of that tangent, it's a 1 over x. It's still x to the negative 1, but you can kind of think of it this way when you write it. So we're going to be doing the derivative first of that 2 coming to the front for that power rule. So 2 tan of 1 over x. Then we need to tack on the chain for the tangent part, so that's going to be secant squared of 1 over x. But then we also need to times that by the derivative of the inside there, which is, remember, that's x to the negative 1, so that's going to be a negative 1 x to the negative 2. So negative 1 times x to the negative 2. And if we simplify this, this will be 2 tan of 1 over x, secant squared of 1 over x. There's a negative out front because of that negative 1, and the x squared goes to the bottom. And then the very last one here, just to play with these powers a little bit more, this is tan with an x squared, that's the argument part, to the negative 1. So we've got tan, we've got an x squared inside, and the whole thing's being raised to the negative 1. So we pulled out the negative 1 power, and then this is tan x squared. That would now be to the negative 2, that whole piece, times the derivative of the inside function. The first one we encounter is tangent, so that's going to be secant squared of x squared. And then we have to take the derivative of the inside of that chain, so that's going to be 2x. So if I simplify this one down, I get a negative 2x secant squared of x squared all over a tan squared, because that negative 2 is going to turn positive when it moves to the bottom, x squared. All right, on example 2, we did A and B in class, so I want to do C and D here. So when we do this one, you might want to rewrite it first. This would be cosine, and then we have sine x cubed, and this is all being raised to the 4th power. So I'm going to be using that y prime is 4 cosine of sine x cubed, now to the 3rd, times, we're going to take the derivative of the first function on the inside of this parentheses. So the derivative of cosine is negative sine x, except, sorry, for us it'll be our guts. So negative sine of sine x, and that part's cubed. And then we want to chain on the derivative of the inside of this. So that's going to be times 3 sine x squared. And then the derivative of sine x is cosine x. So if we wanted to clean this up a little bit, we get a 3 and a negative 1 and a 4. So that's y prime is negative 12. We have our cosine x. We have, this is a cosine cubed, so we could write cosine cubed of sine cubed x. This one is a sine cubed on this inside guy here. So that's going to be sine of sine cubed x. And we also have a sine squared x. So just kind of reorganizing those all together nicely. Now when we do this one, we have to be a little bit more careful because there's pluses going on inside. So when we do our chains, we need to make sure we, because this was all multiplication, so there wasn't really anything to worry about up here. But when we chain these, we want to make sure that we always chain the derivative right next to its piece that you got it from, so the function piece that it was attached to. So this first step would be to pull down the 4. So we have everything inside as the guts. I am going to rewrite that as sine x squared. That's cubed. And then this part now is going to be to the 3rd times. So notice this is being attached to this portion that we're about to chain it to. This would be a 1 plus, and then I'm going to write this as, remember, 3 comes to the front. This would be x plus sine x squared. Now this is a 2. And then we need to chain onto that the derivative of the portion inside that we've ignored, which is times a 1 plus 2 sine x now to the first. And then the sine x is also a base, so we're going to chain right next to that the derivative of sine is cosine. So notice on these portions, when we were chaining them, because this had pluses and stuff involved. So notice the first one, I have my general power rule, kept all the guts inside. Chained immediately next to this part that we took that from, the derivative of that. So we got the 1, and this part right here was a power rule because of the squared. The cubed part outside of that parentheses. So then we reduce that to a 2. And then I immediately chained next to that the derivative of the part inside here. And next to that, I chained the derivative of the sine. So you just have to be careful when you're writing it all out. Okay. And again, I would not try to make that one look prettier. So this right here is finding the equation of a tangent line to a curve with this function at the point 2, 3. First step would be I'm going to rewrite that as 9 plus x to the 4th to the 1/2. And we'll take the derivative of that using our chain rules and our power rules. This is 1/2 9 plus x to the 4th to the negative 1/2 times a 4x cubed, which means that y prime can be reduced to 2x cubed over 9 plus x to the 4th to the 1/2. We're going to plug in our value for the 2. So that's going to be 2 times 2 cubed over 9 plus 2 to the 4th to the 1/2. That comes out as 8 times 2, so that's 16 on top. This is 9 plus 16, so that's 25, so this is square root of 25 on the bottom. So I'm getting 16 over 5 for my slope of my tangent line. So then I do y minus 3 equals 16 over 5, x minus 2 to get my equation. You can multiply the 5 to the other side if you would like. That would make it 5y minus 15 on the left. Distribute the 16 on the right, so that's going to be 16x minus 32. Add over the 15. That gives us negative 17. And then divide everything by 5. So there we go for that one. Okay, for example 4, we've got h is this function that has an f inside, and they gave us 2 different kind of ordered pairs, one for the original function and one for the slope or the derivative function. And then we have, let's find h prime of 1. So the first thing I want to do is write h of x using the square root as a 1/2. So this is going to be 4 plus 3 f of x to the 1/2. So when I take h prime of x, I would have 1/2 parentheses 4 plus 3 f of x times to the negative 1/2 power. Then we need to chain on the derivative of the inside, which is a 0 for the 4. 3 times the derivative of f of x is just going to be 3 f prime of x. Then we want to evaluate all of those at 1. So that's going to be 1/2 4 plus 3 times f of 1 to the negative 1/2 times 3 times f prime of 1. We know that I'm going to write this as a fraction now. The 1/2 is going to be half on top, half on bottom, just like numerator and denominator should be. On the bottom here, we're going to have a square root of 4 plus 3 times f1 is 7, so that's a 7 down there. And on top, I still have times 3 times a 4, because we have that f prime of 1 is 4. So I get, this cancels, so I'm going to get a 6 on top. And then this is square root of 4 plus 21, so that's square root of 25. So that's going to be 6 over 5 as the evaluation. And then we did example 6 in class, so let's do example 5. This is big F of x is f of g of x according to the directions, and it wants us to find the prime of that. So that means we're going to have to take the derivative of this composition, which means that it's the derivative of the outside function with the interior staying the same times the chain, which is the derivative of the inside function. So if we plug in f prime of 5, this gives me f prime of g of 5 times g prime of 5. So we have some information up here in this list. We may not use all of these, but I can replace g prime of 5 with a 6. And f prime is still going to be there, but I can replace g of 5 with a negative 2. And then we know f prime of negative 2 is 4. So this becomes 4 times 6, which is 24. And that's the end of this video.
This conference will now be recorded.
Just one thing, sorry, I had to turn it back on. I went back up and looked at before I was deleting everything, and I realized I did not close a parentheses on this guy. I'm actually going to make it a bracket so you can see it. So this one right here, I meant for this to be a bracket and I forgot to close it at the end. When we were taking these chains, I remember I was saying you have to chain it next to the thing that it came from, essentially. The 1 was separated from this blob by a plus, so when I was chaining this along, this times does not go to all of it. It goes just to this portion right here, and I didn't have a parentheses to end that, essentially. So it didn't make sense the way it was written anyways. So this should have been a bracket around both of those to say that this is one continuous thought, where this is one piece that was a derivative, and this is the chain next to that. This, remember, was a piece, and this is the chain next to this. So they need to continually be chained next to the piece that they came from. So I just wanted to make sure that that was written clearly. All right, now this is truly the end of this video.